Okay, so now example 6, we're going to talk about three space, the R3, right? Three-dimensional space. So if you recall in a previous video, again, go back to your notes where we discussed the subspaces. So in your notes on subspaces, we talked about this example where we divided into categories, right? In fact, I think it was, we were talking about, I might be wrong about this, but I think it was about row equivalents. But I'm not 100% sure. But I remember we went through an example where we had divided this space into subspaces, right? So we showed that there was the trivial subspace, right, with the zero vector. And then we showed that there was one-dimensional spaces, you know, for lines, right? And then we had the two-dimensional subspace. Well, now we can use these terms now that we've introduced them, but we've had the ones with two elements, right? The bases. We wrote out the bases, and we saw that, okay, we have the 0, we have the 1, which associated with lines, and then we had the two-dimensional, which was the two with two elements in the base, and then we had the 3, right? The three elements. So we said all the bases, right? So we now we can show with the previous definition or the corollary and the theorem that now we know that that was exhaustive, right? There's no other bases. There's no other subspaces than the ones we listed, right? Which was those 4: 3 space, 2 space, 1 and 0, right? Also, based on what we've already discussed, we know that we can't have some sort of like in between, like a 1.5 dimensional subspace, right? We can't be in between like lines and planes or well, whatever, you're right. So there's no such thing as like, they're all whole numbers. That's the point I'm trying to make. So that's going to be important as we move forward, because now we know that we can't have, for example, a 5-dimensional subspace in 3 space, right? So we know that there's only 0, 1, 2, and 3. So there's only 4 subspaces that are possible. And that's it.